let's have a look at question 11 from exercise 17C in the Year 11 extension book, because lots of people wanted some help with this one. We're looking at this function, y equals the inverse sine of sine x. We need to start by looking at its domain, range, period, and a bunch of other things so that we can sketch it. So just thinking these things through, let's start by looking at what the graphs of these look like. Now, you can either just have them in your head and picture them, or you can actually draw them. Now, we know that y equals sine x goes along in both directions, like a wave like that. It's got a range of 1 to -1, and it goes on and on forever. So x can be anything. We can take the sine of any angle that we want. So that means that the domain is all real x. It goes on forever in both directions that way. But if we consider, so this is y equals sine x, but if we consider the graph of y equals inverse sine x, it doesn't go on forever. It's got some very firm endpoints there. Sorry, it's a little bit wonky, but you take my drift there. It goes from -1 to 1, and its range is -pi on 2 up to pi on 2. So although we can use any value of x and we can take the sine of it, if we look at what the sine of x can be, well, it's the output of this graph. It has to be between -1 and 1. So you can either see that it's the output of this graph, or you can see that it's the input of this graph. So we're only really getting answers in here between -1 and 1. And when we say, hey, let's take the inverse sine of those, the outputs are going to be between -pi on 2 and pi on 2. So we end up with this range here. Now, does that make sense? I'll go through it one more time. X can be anything, but the sine of x has to be between -1 and 1, and we can see that on this graph, but also we can see on this graph here the same information reflected. So if we're now taking the inverse sine of some value, which now is on the x-axis, between -1 and 1, then the output of that is the range of this graph, and that's what gives us the range here. Now, the period is going to be 2 pi, because sine of x has a rhythmic rotation every 2 pi, it goes around again. So we're going to get answers out of this that vary every 2 pi. So that's going to give us the same period for this graph. Now, is it odd, even, or neither? Well, both of these graphs are odd. So odd and an odd in a composite function is going to make it odd. Now, it says simplify the inverse sine of sine x. Well, if you take the sine of something and then take the inverse sine of that, it's like you've gone through a function machine and then back through the inverse of that same machine. What gets spat out is exactly what went in the first place, which in this case is just x. So this thing looks a lot like y equals x, and that's just a 45-degree line going upwards like that. So it says to sketch it just from -pi on 2 to pi on 2, and if it's the line y equals x, it's going to go up something like this, and it's going to go up to pi on 2 and down to -pi on 2. And that makes sense because we've already reasoned that the range, it can't actually get any taller than that or go down any lower than that. But how much have we graphed here? Well, we've only actually graphed pi width, because we've got half a pi here and another half a pi there. And we've said that the graph is twice that wide. So next it says use symmetry to sketch from pi on 2, or 90 degrees, all the way to 3 pi on 2. So if we keep this going now, we've got pi on 2, and we've got pi here, and then we've got 3 pi on 2 over here. To sketch this section, now it says you can use a table of values if you want to. Not such a silly idea. If you take something like, let's take something like 60 degrees, because we know it's 2/3 of the way along here. The sine of 60 is √3 on 2, but the sine of 120, which is another 60 degrees along, is the exact same number, isn't it? So that symmetry that we get around 90 degrees here, where this is like a little even section, it's even on both sides. Does that sort of make sense? It's got a reflective symmetry around that line, means that we're going to have this bouncing back down like this and coming back to there. Then when it says sketch more of the function, well, we've actually sketched a whole 2 pi of it now, and we've reasoned that it probably has a period of 2 pi. So it's back to where it started. It's literally just going to go up again and down again, and it's going to continue on like that. So hence, use this fact, the inverse cos of t equals pi on 2 minus the inverse sine of t. Now all that is that's just this identity written around another way. The inverse sine of something plus the inverse cos of the same thing is equal to 90 degrees. Now that makes sense because in a right angle triangle, that the two angles that are not right angles, if we call this one and this one these two angles here, they add up to 90 degrees. So we normally will see this with x's or thetas or something in there. They've just put some t's in. Now they've said to use this identity to sketch y equals the inverse cos of sine x. Okay, so we have already up here a nice graph of the inverse sine of sine x. So what we want to do is use this identity to say, all right, well, if we wanted to get the inverse cos of something, then if we don't have the inverse cos of that thing, but we've got a graph of the inverse sine of it, then we could use transformations here to generate the one that we want. So I'm going to take this and I'm going to rewrite it. And instead of using t, I'm going to sub in sine x for t. So let's go ahead and write that down over here. We can say that the inverse cos of sine x, not the inverse cos of t, but sine x instead, is equal to pi on 2 minus the inverse sine of not t, but again, sine x. So see, I've just subbed in sine x for the t there. Now, why have I done that? Well, I've already got here a graph of y equals all of the right-hand side. So if I want to graph y equals the left-hand side, because they've asked me to sketch y equals the inverse cos of sine x, then I've got a bit of a workaround here because I've already got a graph that's close, and I can see that rather than graphing this directly, I can use this graph. I can transform it by reflecting it around the x-axis, because this will just flip it upside down, and then I can add pi on 2, which is just going to lift it up pi on 2 units. So let's start by tipping it upside down first. If we take this blue graph here, which I've just redrawn a little bit more neatly, and that's the graph that we drew originally, that's our original question. If we flip it upside down, or reflect it vertically, it's going down and then up and then down and then up, something like that, and going on forever in both directions, then what we've just graphed here in red is y equals the negative inverse sine of sine x. Okay, so that was quite an easy transformation to make from our blue one. And now to graph this one in green, we just have to graph all of this here, which is we just need to lift it up pi on 2 units. So let's do that in green then. Now pi on 2 is a nice round number here on our graph, so it means that the high points, instead of being at pi on 2, will be up at, the high points in red won't be at pi on 2 anymore, they'll be up here at pi. So I'm going to have a high point here and here and over here again. And the low points won't be at negative pi on 2, they'll actually be at 0. So they'll be here and here, looking at the red ones. And so now I can just go ahead and graph this function in green, and this is y equals, now I could call it negative inverse sine of sine x plus pi on 2, but that's equal to this, so I could also just call it the inverse cos of sine x. And I used this graph to generate this one.